depends upon the crystal structure. Depends upon the crystal structure. Tomorrow, in the tomorrow class, I will tell you that there is something called atomic packing factor. There is something called atomic packing factor. There is something called atomic packing factor, APF. What is atomic packing factor? Percentage volume of the material covered by the atoms. Atomic packing factor is the percentage of unit cell covered by the atoms. So I will tell you how to calculate tomorrow, but little bit information you should have today. So you remember a thumb rule in material science that higher is the atomic packing factor, higher will be the density. Higher will be the density of the material. Higher is the atomic packing factor, higher will be the density of the material. Okay. So now martensiite is having body centered tetragonal structure. Body centered tetragonal structure, popularly known as BCT. Its atomic packing factor is low. Its atomic packing factor is low, so density will also be low. Atomic packing factor is low, so density will also be low. Okay, na? Now comes perlite, or let us say austenite. Austenite is having face-centered cubic lattice. Austenite is having face-centered cubic lattice. And you will come to know that FCC crystals are having highest ever atomic packing factor. It is having highest ever atomic packing factor, so density will be high. So density will be high. Austenite is having FCC structure, density will be high. Martensite is having body centered tetragonal structure, BCT structure, density is low. Okay, na? Now you perform one experiment. Perform one experiment at your home. Okay, so what is the experiment? What is that experiment? That you take one glass bottle. Take one glass bottle. You fill with water. Tight it. Fill complete with water. Tight it. And after that, in the evening, after tightening the cap, put it in the freezer. Put it in the freezer. So in the morning when you wake up, you know what will happen? This bottle will break. This bottle will break. You know why the bottle will break? Because water is having density 1000 kilograms per meter cube. Water is having density 1000 kilograms per meter cube, and ice is having lower density. Ice is having lower density. Just a minute. Just 1 minute. Yeah, it is approximately 918 kilograms per meter cube. Actually, there was one message I was checking because yesterday night I slept off. I got up only 20 minutes before. Okay, na? Because I've taken bath and just enter into the class, your class. So, glass bottle, you filled with water, tighten it, put in the freezer. So, in the bottle, initially there was material of high density. Over a period of time, this material converted into low density. This material is converted into low density. So the volume will expand. When the material is going from high density to the low density, its volume will expand. Previously there was water, now there is ice. So material is going from high density to low density, so volume will expand. And due to volume expand, this bottle will break. So why the glass bottle breaks? Because the material inside the bottle is going from high density to the low density upon freezing, upon decreasing the temperature. This example everybody understood, na? This example everybody understood? This example everybody understood? Okay. Now there is one TTT diagram. Okay. Suppose you have taken one specimen of austenite. You have taken a specimen and taken to a temperature at which austenite is stable. You have taken one specimen and raised the temperature of the specimen so that austenite is in the stable condition. Austenite is in the stable condition. Now this sample is quenched. This sample is quenched at a rate equal to or higher than critical cooling rate. Equal to or higher than critical cooling rate. This sample is quenched at a rate equal to or higher than critical cooling rate. So you know what may happen? Cracks will appear during quenching. Cracks will appear during quenching. Now, why cracks appears during quenching? Why cracks appears during quenching? Reason is exactly same. Whatever example I have discussed with you here, na bottle example, reason is exactly same. Whatever example I have discussed with you. So now, why the I will dictate this particular point. So please hear carefully. This is the austenite sample. When we are quenching in any medium, surface and core means center. surface and core will experience different cooling rates. Surface and core experiences different cooling rate. Okay? Because surface comes in contact with the quenching medium. Surface comes in contact with the quenching medium. So immediately it will come to room temperature and become martensiite. So surface this is the cooling rate of surface. Surface, because it comes in contact with the quenching medium, so immediately it comes to room temperature and becomes martensiite. Okay, na? But at the same time, this is the cooling rate of core. I think we have to draw with a firm line. And this is the cooling rate of core. At the same time, when the surface was martensiite, core was still austenite, because here in this region it is all austenite. When the surface was martensiite, core was still austenite, because surface and core are having different cooling rate. So when the surface was martensiite, core was still austenite. What I discussed here, austenite is having high density and martensiite is having low density. So now after some time core converts into martensiite. After some time core converts into martensiite. So core will go from austenite to martensiite, means high density to low density. After some time, when the core converts into martensiite, so the central material is going from high density towards low density. So core volume will expand. Core volume will expand. Surface is rigid because at the surface there is martensiite. So when the core volume is expanding, there will be cracks on the surface of quenched part.